done so far in order to achieve that, and how we see this impacting the community at large. So to start out, there have been a lot of advances recently, specifically on the mass spec side of proteomics. Mass specs have made huge leaps in the past decade in terms of their sensitivity, their selectivity, their accuracy. But at the same time, if you look at the proteomics workflows that come to us in the literature, almost all of the advances are on the mass spec, the instrumentation side, or else they're in the software. Very few of the advances that have been made in the past decade are actually in the sample preparation side. And this is an area that we think there's a lot of opportunity to improve things in, to bring this up the same way that the instrumentation and the software implementation has been brought up. So looking at a typical protocol that you'll find in the literature today, you'll see that it's a rather long endeavor. After your affinity, which can take as little as 2 hours or could be an overnight protocol, you have to wash and then usually elute your isolated protein of interest before reduction, alkylation, and then again usually an overnight digestion before you're able to put your samples onto the mass spec. Now for certain proteins you have truncated protocols that operate more quickly, but in terms of general protocols there are very few generic protocols that work for most proteins that are any shorter than this. And that was an area that we thought needed to be addressed. Our goal when we moved into this space was to get something that was a lot simpler, where you could essentially go from beginning to end, ideally in a single tube, and in a very short period of time, something that could easily be accomplished in the same day, all in one day at the bench. So what we're looking for is we're looking for something that's simple. And it has to be reproducible. We have to make it in a way that is reproducible for the user. It needs to be fast if you're going to finish your entire workflow in one day. And it needs to be standardized, because that's the only way we're going to enable accuracy and sensitivity necessary in order to move mass spec from being a niche application to being as broad or as widespread as we would like to see it, and as its capabilities deserve. So we started out looking at the digestion step. And digestion has normally been one of the largest bottlenecks because it is usually an overnight step. And it's also usually a major source of irreproducibility, whether it's in liquid handling or in the amount of trypsin or in the digest time, or simply in varying complexities of sample matrices that cause a lot of variation within your results. And one of the things that makes it so time-consuming is that in order to achieve a good tryptic digestion, you normally need to keep enzyme concentration low in order to avoid the autolysis of your trypsin. Instead, we looked at immobilization as a way of preventing autolysis. If we immobilize the enzyme, then the enzyme no longer can cleave itself, and this allows us to fit a lot higher concentrations of enzyme into a smaller space and drive that reaction forward at a much higher rate. At the same time as eliminating autolysis, the immobilization protocol we designed also serves as a way of thermally stabilizing the trypsin. This allows us to perform digestions at high temperature, therefore achieving a simultaneous denaturation and digestion. This is advantageous because no longer do you have to perform a denaturation step which is then stabilized by reduction in alkylation, but instead you can rely on the temperature during your digestion to perform the denaturation for you while the protein is also digested by the trypsin. In doing so, we were able to go from a sample undigested to digested within about an hour at 70 degrees Celsius, skipping these reduction and alkylation steps entirely. Now this time varies from protein to protein, but all in all, we've taken you from protein to LCMS, ready for injection, in about 60 minutes. And this is we called this product Flash Digest, or FD for short. And looking at digestion times for various proteins, we can see that some of them digest very quickly, in as little as 5 minutes or less. Some of them take a little longer. But even proteins in plasma, you'll notice that we have IgG and 50 microliters of plasma there, are still digested in about an hour. Now, there are certain proteins that are particularly resistant to digestion, even at high temperatures with high concentrations of trypsin, such as thyroglobulin and C-reactive protein. One of the things we noticed here is that even when we're accelerating this digestion, we see huge variances in time. And this indicated to us that the typical overnight protocol was not as universally successful as had previously been believed. That in reality, some of these proteins, such as C-reactive protein, probably actually required something more like 72 or 96 hours to achieve complete digestion at 37C. A protocol which simply isn't done because of the time-consuming nature, as well as the amount of trypsin required. Additionally, this leads us to the idea that incomplete digestion probably affects some assays significantly more than others. And we're seeing this more and more in the literature as people investigate quick-release versus slow-release peptides and their impact on quantitation, especially in looking towards the clinical space. So are we really seeing everything when we perform these digestions according to the typical protocols? Well, we looked at an older, well, not too old, but an older method of performing thyroglobulin digestion. And this method involved reduction and alkylation, followed by a 4-hour digestion, at which point trypsin was re-added to the digest, and it was digested for another 16 hours overnight. And following this protocol, we saw a relatively strong signal for the 636 peptide. But for the other two peptides, there was very little signal. And so in the paper that this was pulled from, the 636 peptide was, of course, the focus. However, we noticed when we used Flash Digest that we saw not only the 636 peptide in greater signal, but we also saw an abundance of the 475 and the 604 peptides, showing that these were accessible quantitative markers for thyroglobulin, assuming you were achieving a complete digestion. And these all reached plateaus in 3.5 hours with the Flash Digest. We also looked at C-reactive protein, which has been by far the most difficult protein for us to digest. Initially, we worked with a NIST protocol that performed not only one overnight digestion, but actually 2 overnight digestions. It's a 48-hour protocol. And in comparing it to Flash Digest, we still saw that there was significantly more signal than was being obtained with the typical solution digest. And this leads us to conclude that there are proteins out there, and some of them are key biomarkers that are very difficult to digest and are not reasonably achievable using the typical overnight protocols. And so it is our hope that something like Flash Digest can be incorporated to be a more universal solution by which we can achieve greater sensitivity of these proteins. Of course, many samples don't come pre-purified, and sometimes you don't want to have to move through the purification step. So we looked at analyzing immunoglobulin G in various plasmas, looking at monkey, mouse, and beagle plasmas, and we found that we could get accurate quantitation in plasma down to about 1 microgram per mil without any pre-treatment cleanup or any of the like. However, by the time we get down to 1 microgram per mil, we're still limited by sample complexity. There's enough background noise from the plasma that we can't see concentrations any lower. And it's at this point that we need to revisit how many steps we're including. As seen in the earlier protocol, many of these workflows start with a cleanup step. They pair the high selectivity of antibodies or other methods of affinity capture with the high resolution of your LCMS. And so we designed a method of doing not only the digestion, but also the immunoaffinity step, and coupled them together in a single product, which we decided to call Quick Prep. And in this product, we co-mobilize avidin and a temperature-activated thermally stable trypsin so that you can perform your capture, your cleanup, and your digestion in the same tube. So once your antibody is bound using biotin to the avidin, you simply load your antigen, as you can see by our highly complicated and very expert graphics here. The antigen will bind at room temperature, and then using a wash buffer that's been specifically designed to prevent digestion, you can wash away the remainder of your matrix before heating the entire sample up to 70 C using a digest buffer and obtaining your desired peptides from your protein. The process for optimizing this is fairly straightforward. Initially, you would optimize your digest time, as it's the final step of the protocol, by adding a purified sample of your protein to the resin and then watching it at various time points to determine when you achieve your maximum signal, that plateau that indicates complete digestion. Following this, you optimize your capture time by incubating the resin for various amounts of time with your antigen of interest and, of course, an antibody, and then at each time point taking it out for digestion for the predetermined optimal digest time and watching to see when your antigen has fully bound to the resin as indicated by the plateau. And doing this, we found that we're able to achieve a much greater level of sensitivity. Here in the case of IgG, we can see that we've achieved a sensitivity 200 times greater by adding the immunoaffinity step, thus showing that the Quick Prep acts as a robust means of improving our sensitivity and a very simple means of performing immunoaffinity LC-MS workflows. So now we've taken this entire protocol from your serum or plasma all the way to just before you're ready to inject samples on your LC-MS. And we've performed the entire protocol in a single tube, and it takes about 3 hours to go from start to finish, achieving a simple, reproducible, and quick workflow for performing the immunoaffinity LC-MS proteomics. So I'm going to open up the floor for questions. As I said before, we've had some issues with audio, but if you want to ask any questions, feel free to type them into the questions box on your sidebar. In the meantime, I'll go through some of the more frequently asked questions. One of the things most people want to know is about loading capacity. We sell the Quick Prep with the suggestion of a 30 microliter titer of resin per sample. This is sufficient to achieve a very rapid digestion and also has a loading capacity of about 5 micrograms of antibody, which is sufficient for many of the workflows for which you would need an affinity capture step. Additionally, we've heard concerns about native biotin or biotin-like compounds that might be found in your sample or in plasma in advance in terms of the ability to maximize your loading capacity of the resin. And what we found is that even if we pre-wash the resin with plasma, it does not affect the loading capacity of our biotin-related antibody. Finally, some people wonder whether or not they need to add the antibody first before they add the sample. In our workflows, we found that it doesn't matter whether you incubate the antibody with the biotin-related antibody with the sample first, or incubate it with the resin first, or incubate all three together. You achieve the same effective capture in the same amount of time. Seeing no other questions at this point, I would like to thank you all for coming. If you think of any questions later on, feel free to email me. My email is there on the presentation. Additionally, this has been recorded and will be posted online at the website shown below. Oh, we've got a question. Is trypsin the only digestion enzyme? Yes, trypsin is the only digestion enzyme with which we are working at this point. Thank you again for coming. As I said before, if you have any questions, feel free to email me, and I will try and get back to you promptly. Thank you very much. Have a wonderful day.